I just make a short introduction in this compact course given by Valentin Patilea. It's actually my great pleasure. I know Valentin since many years, and in some sense it was my choice to invite him to give this class. And my idea is to invite people which are probably not so prominent till now, but who are doing active research at the top level. And this is definitely the case, and it should be very useful. So Valentin is at present professor of NCI at Rennes, France. He made a rather non-trivial trajectory, starting from Bucharest, then in Toulouse, in Louvain-la-Neuve, and then coming again to Rennes, and changing many different stage before he became the professor and the head of the research group, as they call it. NCI. It's a high school of economics and informatics in Rennes, very top level. I visited this school many times and we tried even to start doing research. And what is really amazing in the activity of Valentin is that he tries to combine very high modern mathematical level with different fields of applications. So this research is close to mine in statistics, in non-parametric, semi-parametric, goodness of fit, time series analysis, and with various applications to biostatistics, survival analysis, or econometrics. So it's very similar. I'm also very much involved in this field, and I'm very confident that this will be very, very inspiring and informative. Okay, now I ask Valentin.
Thank you very much, Vladimir. I'm very happy to be here. Thank you for the invitation.
Yeah, you can close it. Someone, if he wants to come, it's open.
Well, it's for the second time that I'm here in this room. I've been here for a very short visit last year when was a kickoff meeting of the laboratory in December, and it's very nice to be able to come again and speak now to the students. Well, just say a few words about the place where I'm coming from. So Rennes is somewhere south France. If you look at France, like something like that. Here is Paris. Everybody knows Paris. Here is a large concentration of Russian people, and here is my city. Okay. So
is it also, if you on the left side, where is Biarritz? It's another.
Yeah, of course, yeah. Very historical.
Smaller.
Very concentrated. So in this school, so here is it's Rennes. The city. Do not confound him with Reims. Reims is the region of Champagne. So we are not drinking champagne in Rennes, unfortunately. Only cider. Yeah. And in this city there is a school called NCI. In French this means École nationale de la statistique et de l'analyse de l'information. The French system, you have to know the French system there are two types of studies in university studies in France. The regular university, like everywhere in the world. And in France we have something specific that is the so-called Grandes Écoles. Grandes Écoles were created by Napoleon, so a long time ago. And it was designed to train the elite in some sense of the French youth. So the Grande École, if you want to go in a Grande École, you have to pass an exam. At the university, you don't have. You just go. And perhaps the most famous Grande École, you are École Normale Supérieure. There is one professor from École Normale Supérieure here that will give a lecture in a few days. Polytechnical Institute is École Polytechnique, usually called X, and so on. Among these écoles, you have perhaps certainly less famous écoles that are dealing with specialized topics, and one of them is our school, together with a sister school in Paris called SAE. By the way, Sasha Tsibakov is working in Paris in SAE, which is a sister school to SAE. So our school is specialized in statistics. We are training students for 3 years, only statistics. And then when they get after the master level, they get a degree in statistics. And then we have something like 75, 80 graduates every year. So we have 75, 80 diploma of engineers. And at this present moment, we are the only school in France to do this degree, engineering statistics, which is highly recognized on the job market. Unfortunately, not so much for doing PhDs, but it's not a problem to find jobs on the job market because statistics is used in many places. So this is inside this school. There is a research structure that is shared by SAE and SA. And this is CREST, Center for Research in Economics and Statistics. It's a quite well-known research laboratory in economics, and now it's becoming increasingly recognized in statistics too. So this is about where I'm coming from, and if you have questions about our school and about our research structure, please do not hesitate to.
Is the CREST independent or it's a part of CNRS?
Well, I already tried to say that the French system is complicated. Well, this is a very, very deep question. Very, very deep question. It's a very deep question, and the answer is today no, but after January 1st probably will be yes.
Part of CNRS?
Well, not part, but recognized, levelized. This is a very, very deep question for the French organization. Okay, so as Volodya said, I am very much interested about applications and interactions between fields. And what I try to present here is a kind of overview of some problems. I will start from things that are very well known, and perhaps tomorrow and the day after tomorrow I will come to problems that are more or less open or very, very new. And it's about model checks. So I will try to give you a flavor, just in case you do not know what this is about, to initiate you a little bit, just in case you are not aware, about topics related to model checks. And of course we can discuss very detailed aspects of the presentation, but the presentation will be more methodological than technical. We'll try to understand things, and then we may get into the details if you are discussing during the breaks tomorrow morning or So the title of my presentation is Non-Climatic Checks of Conditional Moment Restrictions. And the outline of the presentation is the following. First, I will try to persuade you that this is an important topic to talk about. And I will present some usual approaches for this. Then I will try to to present one of these approaches in more detail, what I call kernel smoothing based tests. And then will be when we will understand a little bit what are the properties of such tests, we will see that kernel smoothing tests suffer from the so-called curse of dimensionality. Now we know very well because we had lectures with Bologna and other prominent people here about kernel smoothing, and you know that when you are smoothing in high dimensions, you have the problem of curse of dimensionality. And the third chapter will try to give a solution. Of course, there is no miracle because you cannot avoid the curse of dimensionality, but maybe in some situations you can do things. So the third section will talk about an idea of avoiding smoothing in high dimension by smoothing in one dimension and using projections of high dimension vectors in one dimension. So this idea will be then extended to functional data models, and this is completely new material in the sense that the problem is quite open how to test functional data models. Functional data models means instead of having responses and covariates that are finite dimensional, you observe curves, either for explanatory variables and for the responses. Imagine just that you're recording the heart activity for one day, or the cerebral activity for one day, or looking at the stock market and looking for the stock all the day. So you get data that are practically in continuous time. So the whole curve usually is resumed to some statistic like mean variance or whatever, and you use these explanatory variables. But of course, it's easy to imagine when you look for your heart activity, maybe you can lose a heart attack just taking the mean and the variance of your heart activity. So the whole curve could be informative. So quite recently, it's a lot of interest to deal with statistical data that are of functional nature. The variables are curves. And quite a lot of papers are dealing with very simple models like linear models or generalized linear models. For instance, if you want to classify individuals, ill or not ill, given some explanatory variables that are functions. And so all these methods, there is very much done in the estimation and prediction direction, but up to our best knowledge, there is no published paper from all the checks to tell you if the model is correct or not. So I will try to persuade you, so coming through perhaps 10 or more, even 15 years of research, that people who are doing model checks, that you may use the same ideas and try to answer to new questions about model checks. So this is a plan of what, and depends on what I would like to talk about, and depending on your reaction and how things go on, I can adapt, I can change the slides during the night, things like that, to adapt to what you would like to see. So, let's go into the problem. So, imagine that you have n observations that are independent copies of a vector, epsilon x transposed, everything transposed. So T is for transposition, and that you are in x for the moment is in q dimension. So these are random variables, random vectors. In general, the epsilons are not observed, but can be estimated from data, usually as residuals of regression models. So the problem will talk for 3 days. It's the following one. How to test that the expectation of epsilon given x is 0 almost surely or not. And this is to be tested against a general alternative like like I wrote here, probability expectation is 0 smaller than 1. So this is a basic question, and a very simple to understand, I hope. And I will try to persuade you that it's of great use in statistical modeling.
But expectation is given over what? What is ensemble over x?
So there is the expectation of epsilon given x.
But you take some random variables. What would be
Epsilon and x are both random
both
variables.
random variables, and then we take this conditional probability and that.
This is conditional expectation. So expectation computed with respect to conditional probability. And this is 0 or not, and I will try to persuade you that this problem is naturally occurs in many, many circumstances. So this problem is equivalent to non-chromatic testing of the goodness of fit. Or in econometrics, people like to say specification of the model. So testing specification. In many, many models that implies on one hand responses and on the other hand covariates. Okay? Just let's go to mean regression models. So what would be perhaps the simplest type of statistical models implying both covariates and responses? And usually what you ask in a non-linear, linear or non-linear mean regression model, you say that y that you observe is a function, a given function up to a parameter m and theta plus some error term epsilon. And what you usually say is that expectation of epsilon given x is, condition expectation is 0, almost surely. I will neglect the almost surely in the writings, but I put it on the first slide, so please imagine that it's always there. Ah, wonderful. Wonderful. Ah, great. Technology. Thank you very much. So, usually in a parametric framework, the function m is given. Just think of this, the linear model. Or the logistic model. The logistic model, the m function is the logic function, and x theta, and depends on x and theta zeros through the scalar product x prime theta 0. So whatever you have in mind as a model, a parametric model from classical lectures or courses you attended, could be written on this way. And theta naught is a finite dimension parameter that is not known and has to be estimated from data. This is usual practitioner job to do. So these are the examples I've just mentioned. So generalized linear models like logistic, but not only, for instance, Poisson regression, whatever you can imagine with G of this kind, depending only on the scalar product between x and theta, and G is given, exponential, logistic, whatever, depending on what you're modeling. It is important to realize that the problem we are addressing here is very different from the usual t-test or f-tests. When you have a linear regression, you have, for instance, 3 covariates, you may ask if the coefficient of one covariate is 0 or not. Then what do? You just estimate the parameter of this covariate and you apply a t-test to see if it's 0 or not. Something else that you could do is to consider that all the parameters, all the coefficients of the covariates and test jointly if they are 0 or not, and you perform a Fisher test and then you test if there are effect of covariates or not. The tests we'll talk about here are very different in nature because the alternatives are not specified. When you are doing a t-test or a Fisher test, the alternative is specified, is inside the model. You just have one more variable, but the dependency is still linear. Okay? You have the alternative. Here, in the way this was formulated, you don't have the alternative. The alternative is quite general. That's why it's called non-chromatic. So it's very different from the usual theta.
I'm just sorry. You see, in the previous slide you have this parameter x belongs to two-dimensional space.
X is a variable, it's not a parameter.
Here is x is from two-dimensional space,
Yes.
right?
Yes.
And the next x, if you take the scalar product,
Of course, yeah. Of
then
course.
q should be equal to t.
Exactly. Exactly. These are only examples. These are only examples. To avoid to ask, in some cases you have more or
they can be different, I understand.
could be different.
In this case,
In these examples, P equals Q, and these are the examples, the usual examples people have in mind. That's true. And another example is quantile regression. Well, a very popular model, that regression model, that is developed since, let's say, the last 2 decades, mostly, is the one where instead of adding an error term that is mean, conditional mean, of 0 conditional mean, you just suppose that the error term is of quantile, conditional quantile equal to 0. This kind of models are very, very popular because of the robustness of this kind of models with respect to the outliers and the residuals. Just think, perhaps the most popular model is when you take tau to be 1/2, and then you call this median regression. But very much, especially since all this financial crisis and all these extreme events that you can observe in our daily life, people are more interested about tau that are closer to 1 or to 0. Depends how you think about that. So the 1/2 is no longer the exclusivity of such models. So just to say that instead of adding an error term that is of 0 conditional mean, just say that it's of 0 conditional quantile, and you specify this quantile by the number tau between 0 and 1. Of course, it's more complicated would be to let tau to go to 1 or to 0, but here will be fixed. In this case, if you define epsilon to be the indicator of this event minus tau, checking the model, checking if this model is correct, it's exactly checking if the conditional expectation of epsilon given x is 0 or not. So the condition on the eta could be equivalently written as a condition of the epsilon, that is, expectation of epsilon given x is 0 or not sure. So you see, we brought the quantile regression equation to something that could be expressed as a conditional expectation. Checking if this model is correct, one more time, is checking that this epsilon has a conditional expectation given x equal to 0. Okay? It's enough to use this indicator function. This I stands for indicator. Usually, like in the previous models, Q is given, for instance linear, you have a lot of routines, of codes available, for instance on the site of Roger Conker, MATLAB and R codes, computing the estimator, and for linear quantile regression. For nonlinear it's more complicated, but solution exists. And of course, as I said, the parameter should be estimated. Like in the previous case. Well, I will talk a bit later about what means endogenous regressors. Let me go to instrumental variable models, where we will talk about endogeneity. Consider a regression model. All these are examples. All these are examples to try to convince you that the original problem that I put at the very beginning it represents a lot of possible work in the statistical modeling. So let's consider a regression model, y equal a function, a given function, w and the parameter plus epsilon. And for some reason, especially in many economics models, for some reason that you don't have the usual orthogonality condition. The expectation of epsilon given w is not 0. There is some interaction between epsilon and w, which makes that this expectation is not 0. If you proceed to if you proceed to least square estimation, which is usually the estimation procedure that people uses, just put this on the other line, take the square, and sum over the sample. This is the usual way, and minimize this sum. This is the usual way people are estimating parameters. Due to this condition here, called an endogeneity problem, usually, sometimes, you will not get correct estimates for your t. And in some cases, in some applications, you also observe some variable x, and you know, or at least you are more confident to say, that the expectation of epsilon given x is 0 almost surely. So now, of course, you get again to a condition of the kind we saw on the first slide. The model would be correct if the expectation of epsilon given x is 0. Well, this I will not mention too much, but if you are very interested about econometrics and economics applications, you may look at on the bibliography and search for the paper of Hansen and Singleton and about the capital asset consumption model, and see that this is usually an example of model I'm talking about here. I said that I would talk about endogeneity regressors. Imagine that now, instead of saying that the expectation of epsilon given w is not 0, you just say that this probability is not tau. But you have another variable for which is true. Then you just replace everything by the new covariant x. Okay, so now let's go a little bit further. These are parametric models that where if you want to check some model, you come back to a problem that I stated at the very beginning to check if the expectation of epsilon given x is 0 almost surely or not. Maybe at this stage, let me say a word, just a word. Perhaps the simplest will be here or in the previous one. At this stage, you may ask, okay, but we cannot observe epsilon because we observe y, we observe x, but we don't have theta naught. But this will always be the case, so I will come back in a second. This will always be the case that epsilon in such models, epsilon is not directly observed. You have to estimate it from the data. In fact, what you will have an estimate of theta naught, and then you make the difference between the values of y observed and the values of m, xi, and theta hat, let's say, and this will be an estimate of your epsilon that you do not observe. And we will see how the fact that you observe or you do not observe epsilon changes or does not change the testing procedure. But for the moment, don't care too much about how to estimate theta. If you really want, we can, I know that I put it in the topics we'll talk about, but let's simply say that you do least squares and you estimate the parameters by least squares in regression models. And this will be the way that you can imagine that you may get proxies of the epsilon value that you do not observe. Okay, let's go now to another example that could be written under this general form. Imagine that you have a non-parametric regression and you have several covariates and you like to know if all the covariates are significant. I said at the beginning that non-parametric regression in high dimension is not very useful because the rate of convergence and the quality of the estimate deteriorates when the dimension is high. So it's not absurd to try to check if all the covariates are necessary in the regression or not. So then, imagine that you have a response variable y and two sets of explanatory variables. The question that you'd like to ask if regressing on the first group is exactly the same as regressing on both groups. So, in other words, is x2 significant or not for the non-parametric regression? Of course, if you take epsilon to be the difference between y and the projection of y on x1, the question, or you may prefer a different type of epsilon, which is exactly the previous one times the density of x1 that is supposed to exist. For people very used with non-parametrics, you understand immediately that I have to estimate this quantity, and multiplying it here by the density avoids denominators. And denominators, you know that it's a kind of nightmare for non-parametrics. Instead of the case where you say that the design is fixed, then you avoid the nightmares. But if you have a random design, then you do not like denominators. Multiplying here by something which does not change the question, the initial question, you avoid estimating denominators. So we will prefer epsilon to be defined in this way and not in this more natural way. So if you take this epsilon to be did, then testing the significance of x2 in the non-parametric regression is equivalent to testing that the condition expectation of epsilon given x1, x2 is 0 or not sure. So this is another example where the initial problem boils down to something that can be written in this way. Are any questions at this stage? It's okay?
Well, this form with epsilon where you have this weight f1, you know, let's consider just discrete measure, not to talk with density. What will be in this case? It will be weights of the corresponding events.
So sorry, I don't understand.
If
x2 is discrete.
Yes. In fact, in your case, this is x1. Because for epsilon, you have formula. So, what will be this case?
So
below. To avoid small denominators, and one to prefer. I just wonder about.
Oh, here you have something discrete.
Yeah.
In this case, it should be simpler. Discrete variables should be even simpler to estimate. To build things, to build residuals. Here the idea is that you have to build the residual. If this one is discrete, I think it would be very easy to see what it is. And you no longer need to multiply by this. I think so. Now the problem comes from the fact that, well, you cannot avoid the problem of smoothing x1, because x1 is exactly what you have under the null hypothesis. The challenge would be to be able to avoid smoothing on x2. And this is something that, if I have time, I'll show you that you may avoid smoothing on x2 and still check something like this. Okay, another example that is closely related to this significance of variables in non-parametric testing is the so-called checks or semi-parametric index models. Well, if you remember my previous slide with parametric regressions, and there was a remark on the dimensions q and p on that slide, because I put p equal to q in all the examples I provided, and if you notice that all the examples I provided, the regression function was some given function that depends on it was something like that. And if you look in in the textbooks of statistics regression models, you will notice that most of the models people use are of this written in this way. But the function g is given. For instance, is the identity function for linear models, the logit function for logit regression, exponential for Poisson regression, and so on. In the statistical modeling between being parametric, from this way, or being non-parametric, looking for the condition expectation of y given on the axis, there is a first compromise to do, is to say that this function g is not known. You accept the idea that the whole contribution of the covariance is summarized in some linear combination, at least with respect in what concerns the condition expectation. Everything is inside, but you do not know what this function g is. This is a way to go to be more flexible. This is exactly the idea behind the so-called index models. So let y be a response variable, and like previously, lambda to be the covariate. And I said in generalized linear models, one usually assumes that the transformation of the condition expectation is exactly linear or affine function, like you see here, with c and beta be some unknown parameters. In other words, you suppose, as I said, that all the information needed for this projection is carried by one direction. Well, next step, as I said, would be to not to suppose known this expectation, and to try to estimate it from data. And then you go to the so-called semi-parametric single-index models. Why semi-parametric? Because on one hand you have the beta that you have to estimate, and on the other hand you have the form of this expectation to estimate, and this expectation, if you want to be more general, that in a parametric setup you suppose that you don't know it and you estimate it non-parametrically from data. You understand immediately the advantage of this, because here, if you want to estimate it more parametrically, you have to smooth in Q dimension. Here, if you accept it, there is one direction beta that concentrates all the information, then you only have to smooth in one dimension. So, these are very popular models that were used since about 15 or 20 years in econometrics. Valentin has very nice contributions in this type of models, and to estimate beta, and then the next question would be, okay, we estimate beta, but now, if we want to go further, we say that all the information carried by X is concentrated in one projection. Next step would be to see if the information is carried in one or two projections. So in other words, you would like to know if indeed this equality holds true, or you should add some more information in this conditioning here. So this is a way to test the goodness of fit of single-index model. And if you denote epsilon to be the difference between y and this condition expectation, then you come back to the original problem we stated at the very beginning. Of course, in this situation and in the previous one with testing significance, the estimation of epsilon is much less trivial, because it will be something like y that you observe, beta that you don't know, and this expectation that you have to estimate also. So this is a little bit more complicated than in the parametric setup, but some solutions exist and could be done. All these examples to try to persuade you that the original problem was sufficiently general to try to look at it and to try to understand how to solve it. So, of course, since it is a non-parametric testing, the basic idea, of course, is to try to estimate the condition expectation of epsilon given x, and to check if it's close to zero in a suitable sense. this is a function, of course, a random variable. Of course, I already mentioned there are two major difficulties to overcome this problem. To estimate epsilon when it is not observed. This is already said. It's rather easy for parametric setup, more difficult for non-parametric and semi-parametric models. And then to estimate this quantity that we have to estimate non-parametrically because we do not specify the alternatives against which we test. So we have to estimate this in whole generality, or almost. We'll see that in the breaking the curse of dimensionality idea, we'll not estimate this quantity. We'll try to estimate something a little bit simpler, but basically, we are looking for this object. And finally, let us notice that you may also extend all these facts to multivariate settings, finite dimension. Imagine that you have several equations. You would like to model, for instance, the conditional expectation, but maybe you want to model also the conditional variance. And then you have a second equation in your model, and you would like to check simultaneously the two equations. The problem is not much more difficult. Let's stay with one dimension epsilon, and keep in mind that it's not much difficult to pass to multivariate epsilons. It will not change very much. And in fact, when we will talk about functional data, epsilon will be able to take values in the functional space. So this will be even more general than multivariate finite dimension idea that I'm talking right now. Okay, what are the possible ideas to deal with the problem? So I introduced the problem. Right now, let's try to understand what would be the possible ideas to deal with this problem. Consider a weight function that is, let's say, positive, a weight function that will depend on x. And it is quite simple to understand that this expectation is 0 almost surely if and only if this is 0. This is easy to see. We suppose that this is positive. So if this is 0, necessarily the expectation of epsilon given x will be 0. Well, why this is nicer than the previous one? Because now you have a marginal expectation. Of course, it's apparently simpler because, in fact, we still have this expectation inside, condition expectation inside, so the problem is not solved. There's no miracle inside. It is quite easy to see that this quantity here, on the left side of the equality, it is exactly the same quantity here. Okay? It's exactly the same. So this equals this. So, completely equivalent. Just take conditional expectation here. Expectation of conditional expectation, you find exactly what this is. So if this is 0, this is 0. If this is 0, this is 0. Okay? It's completely equivalent. So then you'll see in a minute why we like more this writing than that one. So another idea that is a very small variation of the first one is to consider, instead of this problem, to consider this problem. Okay? For the moment, we will suppose that epsilon is observed, and we'll do like it was observed. So to build this expectation, here it will be very easy, because this is the marginal expectation. We take 1 over n sums. Epsilon, we observe it. Maybe W, we know it, who knows? But we don't have this quantity here. We'll come back in a minute. Typically, W, this weight function that was not specified at the beginning, will be to be taken proportional with the density, and in this way we will avoid estimating denominators with this conditional expectation. The second idea would be the following. Based on the following remark, expectation of epsilon given x is 0 almost surely if and only if this is 0, this expectation here, marginal expectation, indicator function, oh sorry, I changed notation for indicator, it was an I, now it's an 1. So x smaller or equal than small x, when you are in q dimension is coordinate wise, so every coordinate. So if you have this 0 all the time for any then the conditional expectation of epsilon given capital X is necessarily 0. Okay? It's clear why? No? It's okay? So, of course, this quantity could be, one more time, epsilon is observed, X is observed, so this expectation could be easily approximated by sample sums. You take the sum over your sample, and you get an easy approximation of this marginal expectation. It's a bit miraculous, because you started with something that is conditional, and then you don't see conditioning no longer here. The only problem is, of course, that you have to do this for sufficiently enough small x's. You have to do it for sufficiently rich set of small x's. Yes?
Excuse me, I think it's not quite clear why these two conditions are equivalent.
If you write this expectation, epsilon, and indicator, x smaller or equal to small x, you take expectation given x. This depends only on x, so this is the same as expectation epsilon given x, indicator x smaller than x. So you have a function of x, and you integrate it on any rectangle, and it's always 0. So necessarily the function is 0. The same. Perhaps it's here you did not understood neither why these two are equivalent. Right? Is it clear? It's the same idea of doing expectation of conditional expectation. Another idea would be to take some function psi that is nicely enough, for instance exponential, and to look, instead, to replace this indicator by some exponential function that is an analytic function, and then to ask for this identity to hold for a sufficiently rich set of D. And of course, if I said analytic, you may change with another analytic function, non-polynomial, and this still will be an equivalence, could be shown to be an equivalence between the two equalities. Here exactly the same idea. You take conditional expectation. So instead of identity here, you have expectation exponential of x prime, x transpose x. So then you get a Fourier transform that is 0 for x in a domain, and by unicity you get that the function should be 0. And the same will happen with other non-analytic functions. Okay, so all these ideas, we could write them in a unified way. Just to say that it's one method. In fact, we can write it in a unified way, but this will not change the problem because the approaches are of very different nature, and we'll understand in a minute. So expectation of epsilon given x is 0 almost surely, if and only if you have the marginal expectation of epsilon times the function of x and some small x in a domain where pi is equal to this function, does not depend on small x, but is unknown with idea 1. Pi is this function, depends on small x, and is given, and pi, again, is known, given, and depend on small x. So, in fact, there are two categories. Even if we can write it in a unified way, idea 1 is very different in nature of idea 2 and 3. Okay. Now let's try to understand how one would build a test statistic for this kind of problem in the two cases, idea 2 and idea 3. Since pi is given, x is observed, epsilon is observed, let's say it is observed, it will be an easy matter. You just have to replace this expectation by something that approaches expectation that is the sample mean. So, now, as I said, we build this test statistic that we have to estimate the marginal expectation by empirical sums. So, we build this mnx as 1 over n sum over epsilon and I p of xi and x, small x, I from 1 to n, where I did not, it was at the very beginning, epsilon and x are IID copies of epsilon, epsilon I and xi are IID copies of epsilon and x. And this is almost equal to this expectation here. In general, epsilon are not observed, and then you have to replace these epsilons by something estimated from data, like the residuals of non-linear regression. And then could be used using some probabilistic tools that you probably studied in other lectures. With a suitable variance estimator for this quantity, you divide and you obtain a stochastic process that is indexed by x. And by the central limit theorem, you may prove under rather weak conditions that this converges to a Gaussian process that is indexed by x. So these are very good news, of course, because then you can use the functionals. You can use functionals of W, and then you'll have the limit of these functionals given by the law of the Gaussian process. For instance, in statistics you have at least, there are two famous, but they are probably with variations. You have two types of functionals that you could consider. One of them is Kolmogorov-Smirnov type, which would look for the worst small x to look for the largest value of the W, which is the worst small x that tells you that you are not under the null. This is Kolmogorov-Smirnov type. Or Craven-Formizis idea is to consider all the x's and to put all of them in some quantity, like an integral, for instance. So you take the square of the W hat and you integrate everything with respect to x, for instance, with respect to the measure. So the law of these quantities that are random will be given by the asymptotic law, will be given by the corresponding functionals of the Gaussian process G. That is the limit of the process you build. So this is, well, this is an example how to compute the epsilon and to replace with an exponential, for instance, and then you get, this is an example how to build such a statistic. Similar examples can be obtained with an indicator function, and in the statistical and econometric literature, this is linked to the work of Bierens and an econometrica paper in the 90s. Continues further. Bierens used a psi function that is exponential. White and Stichcombe showed that it still works with other analytic functions. And Stude used this idea with the indicator functions in the statistical literature in a benchmark paper in Annals of Statistics in '97, followed by many, many other papers. Since this paper of Stude goodness of it, of the kind we are talking here, has two approaches. One Studer approach, starting with a paper of 96, and the other one based on kernel smoothing, starting with papers written in 97, and on kernel smoothing, the first papers appeared in 96. So starting from 96, it's a huge competition between the approaches that are idea one on one side that will require smoothing. We'll see after the break why do we need smoothing. It's because we do not know the function pi, sorry. And the other approach is given by this empirical process approach that is due to this first paper in statistical of Studer. Now, the empirical process has of course nice interpretation because it's very easy to understand how to build the test statistic. However, there are several drawbacks, and of course, when you try to do some work using other methods, you will remember the drawbacks to the referees. You will remember the drawbacks of the alternative models in order to let you publish, and it's very nice to see how referees have some religion, and they don't sometimes they do not want to get out from the religion. If you don't use their methods, they say that the work is not good. So you have to have some ideas how to persuade them that, of course, the Studer approach is not the only one that works in some sense. So the drawbacks you have is, of course, the critical values. You don't have. It's very difficult. In general, you don't have the critical values in an explicit way because it's given by the law of complicated function of a Gaussian, well, rather complicated function of a Gaussian process. So usually you have to simulate these critical values. And perhaps what is even more problematic from my point of view is that the asymptotic law of the statistic depends on the way the parameter is estimated. This is perhaps easy to understand. Why? Because if you look at the way this is defined, so here you have an error. It's written here. Epsilon hat. That is what, let's consider the case of nonlinear regression. This is nothing else but epsilon I plus m xi theta naught minus m under the null hypothesis. The model is correct. And this is epsilon I. Let's suppose that we can do some differentiation. Differentiate with respect to maybe there's a minus here, plus smaller terms. So usually in a non-parametric, in a parametric setup, the rate of estimation here is of order 1 over square root n. This is exactly the rate at which the empirical process Mn converges. So it's clear that this theta hat minus theta 0 will have a contribution in the variance of this M hat. So, which means that depending on what is the method, of course, in some cases, this contribution could be negligible. But who knows? It's like in the Kolmogorov-Smirnov test. In the Kolmogorov-Smirnov test, if you want to test against, if your observations are Gaussian, not Gaussian standard, but Gaussian, you have to estimate the mean and the variance of the Gaussian distribution, and then the law is no longer the same. The critical values are no longer the same. So it is exactly what happens here. So the asymptotic loss of the statistic depend on the way the parameter was estimated. And of course, you still have to do some resampling, for instance, to estimate the critical values. Now, this was a competing approach, the one based on empirical process. Now we go to the, an approach that is based on smoothing. I don't know how you organize. Yes.
Yes, before we move to smoothing. So there, when we choose this function phi or psi, so you mentioned that it can be indicator, exponentials, or
Yes.
other analytical functions. So
Yes.
what is the rule, how to choose, or what are the best way, or among those families?
Yeah, the choice of the function, could change your. Maybe you can improve the power by changing different. You may think at a class of functions and you choose in some sense what would be the best function with respect to the power, if you want to be powerful against some alternative. For the level, I would say I don't see how to improve with a particular choice. The level, I think it's very complicated. Might be. If we look at higher order asymptotics of the level, maybe some functions would be, maybe some functions would be would give more accurate levels, asymptotic levels. I'm not aware of any study of a choice of functions psi. I would say that could be studied. You put these functions in a class, you try to study with respect to the level, how accurate, and with respect to the power, but I would say what is more interesting anyway, because in any case you have to resample, so the level you don't care too much. Perhaps the most challenging and the most interesting would be to choose the best function with respect to the power.
Yeah, I guess so.
So,
Another way would be, because you are doing testing, so if you select different size, you just will get different tests. And actually you can apply all tests together, somehow aggregate the tests. This means if you are not confident that this particular psi is a good one, you can try with this and that and with another one, and then you just have to correct for multiplicities. I mean, it's a relatively small price because you just increase the probability of the first kind a little bit, but then you are much more powerful because psi determines your sensitivity to alternatives. So in this sense, this is way, and actually this is my old result that you only pay log of the sample size for this multiplicity. So this is called adaptive testing.
an alternative way we'll be able maybe to understand, looking at a little bit differently at the smoothing test. Smoothing is in some sense a way to consider a family of functions. And if you look at some data-driven choices of the amount of smoothing that is on the bandwidth, then it's like looking for a kind of optimal function in a class. This is another possible concept. So,
if I can add, sorry,
yes.
something similar, so maybe it's some guidance for choosing mu in grammar misses. Like in practice, what shall I take?
well, you have other situations, like for instance, Anderson valuing statistics, where you like to put some more mass to some regions. This could be done. I think this is not a problem. These are basically two types of statistics, but then you can consider a weighted version of the chromosomes, and then you can privilege some regions that you believe are you need to privilege with respect to others. So, Vladimir, shall we take a break? In this case, there was a break.
Optimal time. Okay, let's have a break.
Yes.